Welcome, fellows, lecturers, and panel members. I'm George Crabtree. I'm the director of SISE. Welcome to this year's 10th edition of SISE. This is our 10th year. Usually a 2-week intense experience with about critical thinking on energy, present and future. This year, because of coronavirus, we're trying something new. We're going to condense to 1 week and become virtual. So we'll have 2 sessions each day and a couple of more optional informal evening sessions to help build the feeling of community that we usually have at SISE. We have 64 fellows whom Thomas has carefully chosen from around the country and around the world. And the fellows will engage our speakers and panels in critical conversations on energy and climate change. They'll join our network of 500 alumni around the globe, as we call them. We refer to ourselves as the best nerds on earth. In addition, we have for the first time in a decade opened many of our sessions to the public. And we know from looking at our screens that there are several hundred of you present now on virtually. We will also record our sessions and post them on our website so you can look at them later if you'd like to. So we stress critical thinking, looking at information and drawing conclusions. This skill is not often emphasized in traditional university learning, but it's essential to creating and maintaining a vibrant creative society, exploring the frontiers of human knowledge and ingenuity. So we will present perspectives for the SISE Fellows and our broader audience to absorb, to analyze, to criticize, to dissect. And then we hope that the fellows will integrate these with other perspectives to form a worldview that prioritizes action. So this, of course, takes longer than the week or 2 weeks of SISE, but after 10 years, we found that this program helps plant and nurture the seeds of lifelong critical thinking that enable our fellows to take effective actions, not only at the voting booth, which is very important, but also in their professional careers and their personal lives. So we're very fortunate to have a wonderful lineup for this session this morning, starting with Stephen Chu, the former Secretary of Energy under the Obama administration. Let me take a minute to introduce Steve, and then we'll ask him to give us 8 to 10 minutes, maybe a few minutes more of perspective, and then we'll have some questions from the fellows. So Steve comes from a family of highly educated scholars and white-collar professionals. His parents arrived in China during World War II to study at MIT, found that they could not return home. So instead, they became US citizens and raised their family in the intellectual tradition. For example, Steve taught himself to play tennis from a book as a young man. He never learned to speak Chinese, and Steve, you can correct me if I'm wrong, because as I understand, your parents always spoke English to the family. So Steve was awarded the Nobel Prize in Physics in 1997 for his work on laser cooling, part of his postdoctoral work at Bell Labs. He moved on to Stanford and was appointed director of Lawrence Berkeley National Laboratory in 2004. And perhaps many in here know him as the 12th US Secretary of Energy, serving under President Obama, 2009. He's now back at Stanford as the Keenan Professor of Physics and Chairman of the Board for AAAS. Steve, I have some more here, but I think I won't say it. I'll let you introduce yourself, and please give us your perspectives.
Hey, thank you, George, and thank you all for attending. First, I want to thank the University of Illinois Chicago and the American Energy Society for sponsoring this Summer Institute. One small correction in my bio: I did the work at Bell Labs, the seeds of which led to a Nobel Prize, when I was a department head, not a postdoc.
Thanks.
But anyway, all right, let me just begin. This is going to be essentially a history lesson. There's a few predictions in climate, but mostly history. And why do we study history? A very famous quote from is that those who do not remember the past are condemned to repeat it. Now, I'm sure you've all heard of this, but you probably less popular, this Dan Wilson cartoon, you will make the same foolish mistakes you have made before, not only once, but many, many times again. And so that's what we're going to do, and that's what we're doing. In any case, let me also point out something I'm sure you're all familiar with. On the bottom part, you have a measurement of the temperature rise going from the present day, that's 0, going backward 800,000 years. These are so-called ice core samples in Antarctica. And you have a brief warm period, but before that, there was an ice age, and the last brief warm period is about 1.3 degrees C higher. Methane and carbon dioxide is measured by actual gas trapped in the glaciers. And so here's where we are in CO2. This is a little out of date. We're now at 412 parts per million, and we're over 1,900 parts per million methane. All right. So if you look at this and you say, well, about this period of time, Neanderthals roamed the world, and about this time, Homo sapiens appeared. But it's fair to say, for this period of time, we can't blame it on the Neanderthals or on these Homo sapiens, because they were just too incidental. Now, why are those changes in carbon dioxide? Let me go back to this. You see that CO2 is highly correlated with temperature, and these are natural causes. So you can ask, why is carbon dioxide different today than it was going back 800,000 years, and indeed going back 100 million years ago? And the answer is that there is some smoking gun evidence, and many people don't know about it. It's due to human activity. And let me just briefly explain it. I'm going to talk about isotopes. Carbon has many isotopes. It has a common stable isotope, carbon-12, but it has another stable isotope, carbon-13, and a radioactive isotope, carbon-14. And so here I show a plot on years from 1750 to 2005, where you see this is the rise of carbon dioxide. Showing colors. This is the rise of carbon dioxide, but this is the ratio of carbon-14. As you see, the carbon-14 is going down, and similarly, carbon-13 is going down. So what's the cause of that? Well, carbon-14 is made in the upper atmosphere due to cosmic rays that spray out make a lot of neutrons that absorb, and it turns nitrogen into carbon-14. And so these are produced in the upper atmosphere. The carbon-14 mixes with everything on the Earth, including all living matter, and you and I have carbon-14 in our bodies. But suppose we die and we're buried in a very well sealed off coffins, and we're sealed off for 50,000 years. Well, carbon-14 has a lifetime of 5,700 years. We exhume you and me, and we put us in a fossil fuel plant, we burn us for energy. So just proper recycling, we have no more carbon-14 in our bodies because it's all decayed back to nitrogen. So if you take a lot of fossil energy, that is carbon sequestered from the environment, and put it into the atmosphere, you dilute the carbon-14. That ratio decreases. All right, what about carbon-13? Related, you have plants, and plants do photosynthesis. They take carbon dioxide out of the atmosphere, and they turn into biomass material. And their chemistry is very exquisite, so they prefer the ordinary isotope, carbon-12 to carbon. They prefer carbon-12 to carbon-13. And because of that, if you take all that plant material, fossilize, burn it, you dilute carbon-13. And similarly, you see all this happen. Okay. Now, you might wonder why the data runs out here. In fact, it doesn't. What happens after about 1950 is there's atmospheric H-bomb testing. The neutrons from H-bombs make a lot of carbon-14. They peaked very rapidly and started to decline. And now we see the decline of this atmospheric testing of hydrogen bombs as also being consistent with, quantitatively consistent with how much fossil fuel we're burning. So let me say it again. We burn fossil fuel, got no carbon-14 in it because it's been sequestered for too long, many, many lifetimes. So you dilute the carbon-14 to carbon-12 ratio. So this is what most scientists regard as the smoking guns, that this is carbon that has been sequestered for a long, long time. Let's go back in time, more history. Now here's the present time, and now we're going back tens of millions of years, 10, 20, 30 million years ago. And why do I have that? It's stupid messaging. Okay, anyway, so what we have here is the measurement of oxygen, ratio of oxygen 18, an isotope of oxygen, stable isotope, to oxygen 16. It turns out again that the incorporation of these two isotopes of oxygen into seashell critters depends on the relative abundance of oxygen 16 and 18. Oxygen 16, it's lighter, it evaporates more easily, it precipitates. And so when you see variations in oxygen 16 to 18, it means that you can tell how much, this is a measure of incorporation of oxygen 16, oxygen 18. So that's a measure of temperature that goes back beyond ice age samples, okay? So these are seashell critters, and now we see temperatures that range from, you know, the scale there, 0 to 5 degrees centigrade. But remember, there's a strong correlation between carbon dioxide and temperature. Temperature now measured in oxygen isotope ratios. What was the carbon dioxide doing? You go back and look at the isotopes of carbon being incorporated into plants, and what you find, lo and behold, is that a very recent paper, and it's very consistent with all the other papers beforehand, it actually is published this last month, and what it says is that in the last 23 million years, the entire Miocene era epoch and to the present time, the carbon dioxide in the atmosphere of today's Earth is higher than it's ever been in the last 23 million years ago. And here you have the present value of CO2 in the atmosphere. This is what are projected to be perhaps in more, it's quasi-optimistic business scenario, and perhaps maybe here's where we might be if we blunder along the same path. All right, so what have you just heard? Strong correlation between carbon dioxide and temperature. This carbon dioxide is different. It's caused by humans. But that correlation actually does support the greenhouse gas effect, which means if the carbon dioxide goes up, the temperature will go up. So if we're higher than we were in the last 0.5 million years, why is the temperature as high as it was a long time ago? What's a long time ago? Well, this is 23 million years ago. This is where Antarctica melts. This is where our present temperature is about now. And so the reason is it takes a longer period of time. Why? It's simple. The oceans, the deep oceans are very cold. Anyone who's done any scuba diving or snorkeling know you go tens of meters below the surface of the ocean, it gets very cold very fast. It takes a lot of time to warm up the cold ocean. So the effects we're seeing today are nothing compared to what we've already done. So that's our history. So here it is, another graph. On the x-axis, I'm plotting time, 1750 to the present time. On the y-axis, cumulative emissions. Well, let's explain cumulative emissions. First, 3/4 of the greenhouse gases has occurred only in the last 65, 70 years. And although Yogi Berra did not say this, he could have. It said that if you don't change direction, you will end up where you're heading. Where are we heading? We're heading over here. And at the current emission rate, this is CO2 equivalent. So it not only includes CO2, it includes methane, it includes N2O, it includes hydrochlorofluorocarbons, all the greenhouse gases, which are about 50 gigatons per year of equivalent emissions. And at that rate, we pass this line in 14 years. By the way, that last warm period that was 1.3 degrees higher, the sea level was 6 to 9 meters higher. Again, it's a fossil record, not a prediction, because you just look at the critters who lived at the edge of land and ocean around the world, and you find, you isotopically date them, and you find that's where the sea level was. So the UN goal is to keep our sea levels at the 6 to 9 meter higher level. Okay. All right. Now, something I said even before Secretary of Energy, but often as Secretary of Energy, I quoted Sheikh Yamani, who said, "The Stone Age came to an end, but not for lack of stones. The oil age will end, but not for lack of oil." And what he meant by that is you go from the Stone Age to something better when there are better solutions. You begin to use metals. But what is not said is if you don't find a better solution, which is better economically as well, the oil and gas will be used. It will come out of the ground because there's trillions of dollars worth of money under the ground. And so now you can think, okay, we just stopped using gas and oil, but it's not so simple. What is good news is a lot of progress is being made on electric vehicle batteries. And so the electrification of light-duty vehicles is going to happen. It might take a couple of decades, but it is going to happen. But that's just the start. It's carbon-free, cost-effective sources of chemicals, plastics, materials like cement and steel and airplane fuel. Those things we don't have solutions for yet. Don't think that the oil will run out. The technology for finding and extracting oil and natural gas has improved almost as fast as wind technology. And so what has happened is we're able to find more resources and extract more of them as time goes by. And so I think absence of any effort to decrease their carbon emissions, the oil and gas industry can keep up. And so this is just the worldwide, I mean, you see conventional oil is now been overtaken by unconventional oil. Here's another challenge. We have energy, very inexpensive energy. Wind and solar are fantastically inexpensive now, especially at the best sites. At the best sites, they're cheaper than actually natural gas when the sun is shining or when the wind is blowing. But if we want to get more than 30% renewable energy penetration, suppose we want 80%, then you look at the energy storage needs of the country and the transmission needs of the country and the world. And what you find is that we need amount of energy, it turns out not to be much. If we could store 50 hours worth of energy, both energy, this is energy, and this is power, two things. If we can store that amount, only 50 hours worth, we could get 80% penetration. And this was outlined, all the costs were outlined in a very recent article written by 3 members of former RPE in the Department of Energy. So that's great, only 50 hours out of, there's a lot of hours in a year. But the other sobering thing they said is how much should this energy storage cost on a per kilowatt hour basis? Around $20 a kilowatt hour, somewhere in this range. This is a log curve. This is 1, 10, 100. Here's where lithium-ion batteries are. They're $200 a kilowatt hour. So the cost of storage has to decrease tenfold. And it is not going to come from chemical batteries. George Crabtree and I know this full well, not in the next 20 years. Okay, so we need new storage. We have to relook at pump storage. We have to look at new types of thermal storage, but this is an incredible challenge. All right, let's talk about greenhouse gas emissions. This orange over here is due to fossil fuel burning. It's due to industrial heat, the cement, the steel, all these other things. And this orange, CO2 forestry agriculture, is out here. And then in addition to that, there's methane emissions and there's N2O emissions. About half the methane emissions are due to agriculture and raising animals. The rest is due to leaks in a gas system, leaks in explorations. And you see that if you look at half of this, and virtually all of this is due to fertilizer runoff. So if you look at this, it turns out that of the greenhouse gas emissions in the world, it's actually more than the greenhouse gas emissions in producing electricity. So if you want to decrease greenhouse gas emissions, yes, you have to clean up the electricity, you have to clean up transportation, but you also have to clean up agriculture. And we have another issue that if you look at all the habitable land in the world, you take out the deserts, the oceans, mountains, and half of it is already used for planting crops and for grazing. Also, the animals we use in agriculture are not natural animals anymore. This full circle is the natural lifetime, let's say, of a steer, starting here and going all the way around. And this is the time since birth the animal is allowed to live before it's slaughtered. And so you see the animals are slaughtered in a very small fraction of their lifetime. But it's an amazing thing because, for example, after only 22 to 26 weeks, the average American pig is 280 pounds. This is very fast growing. Broiler chicken's only 40 days. And so these animals have been bred to be very efficient at turning animal feed into protein. And this is an example of turkeys that are slaughtered only 3.5 months after hatching. These are the standard Safeway turkeys. You buy 12, 14 pounds without the innards and the feet. But they're a little bit weird. They're so breast heavy because Americans like breast meat, white meat, that they don't mate. So they're reproduced by artificial insemination. So these are kind of funny natural animals. You compare these turkeys to wild turkeys. Don't really know how old these wild turkeys are, but they look kind of different. The only thing I can say is I know how old this wild turkey is. If you're a wild turkey 101, it's 8 years. All right, let's move on. Let's look at the annual CO2 emissions in world region. It's Our World in Data. It's a great website. And it compares, again, from time 1751 to 2015. And this is the EU 28 at the time when Great Britain was part of the EU. And that's the amount of carbon emissions. This is the United States, and this is China. So the two largest countries are China first, followed by the United States. And both of those are bigger than the EU. If beef and dairy cattle were a country, they would have more carbon emissions than all the countries in the world except China and the US. This is a significant amount of carbon emission from raising the crops, raising the animals, the manure being converted to methane, et cetera, et cetera, et cetera. By the way, we've altered the world profoundly. If you look at all the mammals in the world, and you put the wild mammals on one side, those are the lions and tigers and bears and mice and rats and all that other stuff, you know, 3 reindeer, whatever. And then you put people and the animals we eat on the other side of the scale. It turns out 96% of all the biomass are us and the animals we eat. The world is a very different place. So when people talk about geoengineering and that we don't want to go there, I'm sorry, we've been doing this for thousands of years. So what does that mean? We have to transition as a world of 7.5 billion going to 11 billion, we have to transition to eating less meat, even if you have enough wealth to buy the meat. And also there are meat substitutes. There are Impossible Burger food or Beyond Beef, where you can buy this and it sort of tastes like beef. In fact, I'm a little partial to Impossible Foods Burger because a personal friend of mine started this company. I'm impartial because he called me up and said, Steve, because of you, I quit my job. He said, he was a professor at Stanford, a Howard Hughes Senior Fellow Investigator, member of the National Academy. He said, Pat, what are you doing? And he said, well, you left your job to go work for the Department of Energy. I want to do something about climate, so I'm going to quit my job. I'm a biochemist, so what do I know? I know chemistry. I'm going to make something that tastes like beef. Anyway, another thing, not only eating less meat and having meat substitutes, but there's something else we can profoundly affect agriculture. If you look at certain plants, they interact with the microbes in the soil. Legumes are a prime case. And the microbes actually make fertilizer for the plants. In fact, they're used in the olden days to enrich the soil, so-called crop rotation. And so the question is, can you do this now with fertilizer-intensive crops like corn? And so we're beginning to discover there's a very complex interaction between the microbes and the roots, but it's a chance to use far less fertilizer. But beyond that, you can actually sequester carbon back in the soil. As soon as agriculture started, we've been depleting carbon from the soil. And so we're beginning to study these interactions. But better than that, there are startup companies. And now already in practice for the last 2 years, Pivot Bio is a company that puts microbes that have been genetically modified to actually feed corn. The corn has not been modified so far. And so in so doing, you have eliminated half the fertilizer of the corn with the microbes on the seeds of the corn are on the right-hand side. And when the plant says, I'm hungry, feed me, the microbes oblige and they create nitrogen-based fertilizer for the corn. So we need to do this for all our grains. We need actually to make perennial, but we'll start with this. Finally, let me see about what happens. On the x-axis, I'm plotting electricity consumption, and the y-axis, human development index. And for those of you who don't know, this is a mixture of a country's wealth in terms of life expectancy, education, level of education, and GDP. But it's the logarithm of GDP, because if you're worth $100 million and you're now worth $1 billion, the quality of your life hasn't gone up that much. I think it's gone down myself. But anyway, if you look at the countries, you have very energy-starved, electricity-starved countries living in poverty. They're way down here. And as you gain more and more wealth, the Human Development Index plateaus. And so this is great. This is 4,000 kilowatt hours per person. No, the units are wrong. It's not per person per year, but never mind that. It's about 4,000 kilowatts of average power, and you're in a wealthy country. And then the question is, can the US and China, everybody go down to here based on energy efficiency? The answer is yes. That technology is known. But remember, it's the greenhouse gas emissions from all sources, electricity, transportation, materials, and so on. And they need to go to zero in 50 years. All right. Now, my final moments, I think I'm a little over, but bear with me 3 more minutes. Increased prosperity of virtually all countries is based on recruiting and producing more young workers to support a smaller aging population. And so we see in countries that have shrinking populations, notably Europe, they're beginning to give bonuses to have people have more children. I think it's either Hungary or Poland, one of the countries, if you have 4 kids, you don't have to pay personal income taxes anymore. Okay, they want more, they don't want anybody, they don't want immigrants, they just want more, let's say, Polish people. All right, so there's a name for this strategy. It's called a pyramid scheme or a Ponzi scheme. If you have more young people supporting a smaller fraction of older people, this is great. And you just continue it that way. If you have a smaller young cohort supporting the same number of older people, then you're steady state. But it's easier to have economic growth and balance your budget if you have young producers of wealth taking care of the older people. So leaders are now terribly afraid that you will have a shrinking population. But actually, you don't want a world of 11 billion. There is very natural birth control. When people get wealthy in all cultures, all countries, they have fewer kids. Just a fact. It has a lot to do with women's education. It has a lot to do with late night TV. It has a lot to do with all sorts of things. But in any case, we have to redefine wealth. And as long as you use GDP as a measure of the country's wealth, the goal would be produce more stuff and consume more stuff, because that's what you're measuring when you're measuring GDP. What are you making of value, and you have to consume. So human development index gives a step in the right direction, includes education and health. But I would go further, and perhaps a better definition of wealth would include the quality of your health, quality of life, especially in old age, the level of stress in your life, your social connectivity. And so my message here, and the closing message, is that sustainability requires that we really redefine what we mean by wealth. And so it's not just GDP. If it's not just GDP, then we at least have the goals set in the right directions of more personal satisfaction and happiness. Okay? And so given all these things, the climate threats and risks that are coming true far faster than I thought 20 years ago and 10 years ago, actually give us cause to think deeply about where we're heading in the last 2,000 years. And with that, I'll stop. Thank you.
Boy, Steve, thank you so much. Wonderful overview, very provocative, and certainly a perspective for critical thinking by the fellows. So that was wonderful. We have time for a couple of questions. One question, I think it comes from Palo Alto. You hear people saying, especially Bill Gates, we have to be revolutionary about decarbonizing, do it fast. And you have others saying, well, no, it should be evolutionary. We have the technology, we just have to deploy it. How would you balance these two perspectives, Steve? What are your thoughts?
Well, we have to do it fast. It takes, the world's a big ship, and it takes decades to turn it around, turn around the infrastructure. It's not like changing your iPhone every 3 or 4 years. You build an asset like a utility generation gas plant, it's there for 50 years. You just made the investment, you're going to use it. And so, for example, cars. You can buy a car every 15 years. Great. It's predicted in the optimistic scenarios by 2040, over half the cars will be EVs. That means the other half will be internal combustion engine cars. Oh, by the way, will live another 15 years. So it takes time to make these changes, even if you go very fast. And so you've got to do it very quickly. Evolutionary, yes. Solar power was evolutionary, but you know, evolutionary over several decades became spectacular, just like integrated circuits. And so there could be revolutionary things. There are new ways of heat storage that could really dramatically change things. Don't know. George may know I'm working on a revolutionary battery of sulfur and lithium metal where you can cycle it 1,500 times and get the energy density higher than the current lithium ion batteries. Now, no one's actually succeeded in making this type of battery, but if you make that battery, you can get 80% vehicles on that kind of battery and you won't run out of sulfur. And we've also just published an article, you can get lithium from seawater. So these are some of the things one can do that are more revolutionary. It's not standard technology, but a lot of the revolutionary stuff, in fact, doesn't in the end work. You do both, and of course you need policy.